Hi, everybody. I guess we will start today and welcome everybody remotely connected and in the room. So our guest today is Oliver Buchmüller. He is a professor at the physics faculty of natural science, Imperial College in London. Oliver had his PhD degree from Heidelberg University in 1999. And since then, he joined CERN for different responsibilities. So he was a CERN fellow at the Aleph experiment, then at SLAC with the Babar experiment. Then he was the chair of the CMS analysis review committee related to supersymmetry experiments and so on. And presently he is the PI of the Atom Interferometric Observatory and Network, AION, which is a UK network of universities concerned with building interferometers to detect gravitational waves and for dark matter search. He made important contributions for space proposals to use cold atoms in the context of precision experiments, such as the AEDGE proposal, the STE-QUEST proposal, and lately he was very instrumental to propose this roadmap for cold atoms in space, which was proposed to ESA lately and was backed by a large number of colleagues in the community of cold atoms and others. So we are very happy that you made it here, and the floor is yours.
Yeah, well, thank you, Nasser, for the invitation. It's a great pleasure to be here today in Hanover, in particular with this outstanding weather. I'm told it's always like that, but I seem to remember differently. Yeah, so as Nasser pointed out already, I mean, my background is really in fundamental physics, particle physics. So I'm not a cold atom physicist. So my focus on the presentation here today will be more on the fundamental physics side and how we could use, in particular, cold atom technology and especially atom interferometry to explore open questions in fundamental physics. So that's what I'm going to focus on today. But we also have a representative from AION from the cold atom side, as Richard Hobson, who is sitting here. So let's start with the science case just to set the picture. So I have listed down some examples. That's my personal preference. I mean, I'm sure if you ask other people, they will come up with a different list of open questions in fundamental physics. But it is pretty clear that there is a lot we do not understand yet about the beginning of our universe, the constitution of our universe, and how the whole thing came together. We certainly struggle to understand what is dark energy. We do not understand what is dark matter. And there's many open questions and many different avenues we are trying to pursue, like collider-based experiments, direct detection-based experiments. And I would like to explore now with you the option of seeing whether or not quantum technology, in particular quantum sensors like atom interferometry, could be a valid tool to help us explore open questions in fundamental physics. Now, as I said, I'm not an expert really in it, but if you really look how the evolution of quantum technology came together, then obviously everything started at the beginning of the 20th century with the formulation of, quantum mechanics, the mathematical framework of quantum mechanics. And then over years and decades, first applications like transistors, hard disks, later then also lasers came out. And many people believe that today, starting maybe with the beginning of the 21st century, we have entered what is often being referred to a second quantum revolution. Now, as I said, I'm not an expert, so I'm repeating what people as experts tell me, what is being thought about it. And I think a lot of it started really with the investment into quantum sensors like atom interferometry a decade ago, which now come to a technology standard where we can think of using them for more hands-on applications and potentially also for the exploration of fundamental physics. So this is how I came into the game, by essentially seeing how could you use atom interferometry to explore open questions in fundamental physics. Now, the conceptual idea, I really don't want to go too much into it because it feels like I'm the wrong person to lecture you of how an atom interferometer is operating, because I'm coming from a different field. But I personally found it very illustrative to compare atom interferometry with laser or light interferometry, because this is something I do understand relatively well. This is what I'm teaching my students in Imperial, but also have taught it in Oxford. So a light interferometer basically is relatively simple. You have your active element, that's your laser beam. You operate a beam splitter, then essentially the light takes two different passes, and with mirrors, then essentially you collect the light with the two different passes again in your detection system, and then you're observing light fringes. And with these light fringe observations, you're basically being able to tell if there has been any differences the light has been experiencing in the two different passes as it went along, and then went to the interference patterns. Atom interferometry, in my understanding, is conceptually the same. However, the active element here now become atoms, ultra cold atoms. As a matter of fact, it's not just one atom, but it's an ensemble of atoms. So we're aiming, for example, at AION, but also then for STE-QUEST at the 10 to the 6, 10 to the 7, 10 to the 8 level eventually then in the long term. And then what you do is you cool them down ultra cooled, and then with the help of beam splitters, you are splitting this ensemble in two different parts, excited state, ground state, and then over space-time evolution, you have again your two different passes, and you bring it to the interference patterns in your detection systems. And now you are observing, instead of light fringes, matter fringes, or if you like, atom fringes. But the concept basically is the same. Where the atom fringes, you can then effectively determine whether or not there has been different behaviors observed in the two different passes, which you are bringing then to the interference with the entanglement. Now, let me come to the AION experiment, which is very close to my heart, because that is something I helped establishing and funding, which really brings together the idea of atom interferometry and the application to fundamental physics. To illustrate what AION is about in terms of atom interferometry experiment and how we want to use it, I would like to use an analogy of two atomic clocks to show you how we like to perform a differential measurement. So using atomic clocks because it's easier to illustrate than two atom interferometer sequences, but the concept, at least on a high level illustrative perspective, is the same. So you have your two atomic clocks. You should think of them really widely separated from each other in terms of space. So you lose one laser beam now to synchronize these two clocks. So basically you're bringing the ensemble of the atoms, half of them in the excited state, half of them in the ground state at a given time. Then you start your experiment. Now these clocks pass through space-time, if you like. And at the end of your experiment, again, you're synchronizing the two clocks. And the excited state of these two clocks, because they were passing through space-time, they had an evolution, basically accumulate now a phase. Now, if I'm comparing the two clocks and the phase which has been accumulated between the excited and the ground state, as you can see here, for example, then I would basically make a null measurement if nothing has happened. So this is the two different passes of the things basically that take place. Now, what happened if a gravitational wave would have passed through? And now we are hypothetically assume it would only be having affected one of the two clocks. It's obviously a bit more complicated, but for illustrative purposes, it's relatively simple to do it this way. Then this gravitational wave, because of its strain, so the strain basically is characteristic for the special relativity incarnation of a gravitational wave, because it has a length dilatation and the oscillation as it comes along with it. So it changes the length of the space-time continuum, and that strain basically is the measure of the change of the length with respect to the total length. So it's a relative change of length. Now, because the speed of light is constant, that directly then translates in that pathway to a change of time that one clock has seen. And that change of time is then what I'm actually measuring. Sorry, I should show this here. Or does it actually work? You can see this when I do this, but maybe not from the camera. So if that change of time here basically will be imprinted, now if I'm comparing the two clocks, I will be able to measure in this phase difference delta t. Now from delta t, I can go back to deduce the strain of the gravitational wave and eventually then also its frequency. So it's a direct way of measuring properties of a gravitational wave by simply comparing these two measurements. It's not an absolute measurement, it's a differential measurement by comparing one clock with respect to another, or later two atom interferometer sequences with respect to each other. Now, the interesting thing is that a similar thing can happen at the same time if we're not having a gravitational wave, but if we assume and hypothesize that, for example, we are surrounded by a halo of ultralight dark matter, and that ultralight dark matter really cannot be seen anymore as a particle in terms of an individual thing, but more like a wave character. So you can really describe this, as I will show you later, as a classical wave function. And that classical wave function will couple with your standard model Lagrangian and imprint on the fundamental constants of this Lagrangian oscillations. And these oscillations will be determined basically by the frequency and the mass. So the mass and the frequency of the dark matter candidates are being the same. So they will be imprinting on the constants of the atoms I'm using in order to operate my clocks. And that again will then imprint on that phase, not in terms of the time, but this time in terms of the frequency oscillation, as you can see here. And again, I'm comparing my two clocks. I will be able to measure back this delta omega, which is essentially the frequency imprinted by the by the dark matter halo on it. So we have at the same time, with the same setup of an experiment, the capability of measuring either a gravitational wave via time or at ultralight dark matter candidate via the frequency imprinted on the phase, which is pretty interesting. Now, another interesting aspect in that setup is that because I'm using one laser beam to synchronize my, my two clocks, everything which comes along with the laser noise, the mechanical platform noise in my setup, at least conceptually, will be imprinted on both clocks at the same time. So if I'm comparing the two clocks again in my differential measurement, it will cancel out. Now, this laser phase noise is the limiting factor for laser atom interferometer experiments which have been utilized like LIGO and Virgo to measure gravitational waves. And that's the reason why all of these experiments conceptually need to have a double arm setup. So essentially you run two arms of these experiments with a 90-degree angle to have maximal sensitivity to then compare the two arms to cancel out the laser noise. If you were to use atom interferometry, at least conceptually, you could do two arms, but you don't have to. You could just simply use one arm structure to basically measure then the gravitational waves, assuming everything really cancels out, which is one part of our research program we are trying to pursue. So that's the idea, that this phase noise can be canceled. And that's what we would like to realize in the AION experiment. So it's really a different kind of an atom interferometer, if you want. It's really a relative measurement being performed. So we decided that we would like to utilize strontium as a single photon transition and the clock transition. So to build on our expertise we have in the UK, but also in the US, Match's experiment is very similar. Now, in order to realize terrestrial experiments, and to have sufficient free fall, the two atom interferometer sequences, as you can see here now in the space-time diagram, are ideally being located in shafts or in towers, if you like. So we will start with a 10-meter detector as a prototype where the two atom interferometer sequences are being separated, for example, by 10 meters. But then our ambition is really then to scale it, as you can see it here, to larger dimensions, depending on what kind of shafts we can utilize. First, a 100-meter detector and eventually even a kilometer detector, because sensitivity will scale linearly with the separation of the two atom interferometer sequences. So that's quite important. Now, for AION, and I should probably also point out, this is an R&D program, because we do realize that in order to perform to the level being required to measure, for example, gravitational waves, the sensitivity we need really means that we have to push the envelope of the basic parameter of strontium-based atom interferometer completely new dimensions. There will be large momentum transfers. We are looking at thousands, even 10,000s eventually in the ultimate program. We are looking at squeezing. There's many different aspects we have to push. And we do understand that this is currently not being realized. So a significant R&D program has to be put in place to really achieve this type of sensitivity. And that's basically how we have been pitching AION, the program, to the funding agencies in the UK, not only as a single shot, but really as a full development program over 2 decades, probably even longer, in terms of realizing then eventually the full exploitation of fundamental physics. That's very similar to what we do in particle physics when we are planning big experiments, like, for example, at CERN. We're not planning for 1 year or 5 years. We're really planning here for decades. And I think that is one of the important aspects one has to see here as well. That program is planned for 2 to 3 decades, not just for a couple of years. Now, the first phase, and that's how we have been proposing it, is to build and commission a 10-meter detector, develop the existing technology, and demonstrate that this parameter, as I mentioned to you before, like large momentum transfer, squeezing, number of atoms, can really be pushed in the right direction to achieve that sensitivity. And that was successful, and we have been funded with 10 million pounds, so that's around 12 to 13 million euros to really start kicking off the program. And as a next stage, which we will propose to the government in about a year's time, is then to go into scaling the 10-meter detector to a 100-meter detector with the appropriate site, and eventually, and that will be the ultimate terrestrial realization, is to push it to a kilometer stage. So both for the 100-meter detector and the kilometer detector, we have already started site investigations. So for example, for the 100-meter detector, I will show you later opportunities to build either in the UK, but possibly also in a more international environment like CERN, and reuse infrastructures. And for kilometer detectors, we're actively looking at mines, like the Bolby mine in the UK, but also in Northern Ireland. But then there's also the Gotthard tunnel in Switzerland, which has a 900-meter additional support shaft, which is completely idle and not being used. And the Swiss government already indicated that that could be a shaft where, in collaboration with CERN, which is also hosted in Switzerland, one could build a kilometer detector. So that is now really in preparation. So we're really being serious about that. But ultimately, and that is really where you get most of the sensitivity in this stage program, is we want to bring it to space. This is when you really benefit from the free fall time maximally, from the time to interrogation. And this is when you then get your ultimate sensitivity. But we do realize that such a program is not something which will be happening tomorrow. That has to have stages of terrestrial pathfinders, if you like, along with an interesting physics program. Then hopefully by 2045, we will show you later a mission seeing with cold atoms doing the ultimate exploitation of gravitational wave physics. Now, here's a picture of AION and the collaborators, if you like. AION is really a consortium, now a collaboration, because we have signed an agreement after the funding, which brings together all the big university players and national institutions, most of them at least in the UK. So we have Liverpool University, we have Birmingham, this is Birmingham and the Quantum Hub in Birmingham with Kai Bonds being an active core member of AION, for example. We have Cambridge University with Ulrich Schneider on the cold atom side. We have Oxford University with Chris Foote on the cold atom side, joining the effort and being active core funding members of AION. We have Imperial College, where we are coming from. We're the lead institution. We have to have a lead institution in the UK. We have King's College London, and we have RAL, which is the Rutherford Appleton Laboratory. So we really bring together quite an experienced team of particle physicists, fundamental physicists, and cold atom people. And interesting here is really, I think it's the first time, at least for me, that we see here a quite diverse team coming together. So this is really 60 people, active people in AION today, which are working at the different institutions. And it's really half-half, basically. So half of the people are coming from the cold atom technology side. So there's the stakeholders, if you like, but the other half are coming from fundamental physics side. And these two are coming together now to form a new and unique collaboration. So our idea is that to build in Oxford, in a beautiful, relatively new purpose building, the Beecroft building. If you've ever been there, that you know that Oxford is a very rich university that has costed 50 million. It's a beautiful building being put in place here. And it wasn't easy to find a spot which is, 12 meters high, unless you've been so lucky, like you here in Hanover, that you can build your tower directly into the construction of a building. We were not that lucky, but we were able to identify an idle staircase of 12-meter height, which Oxford was willing to donate to us to build that experiment in it, and conveniently located down at the end, maybe I'll show this better on the next slide, is basically here direct access to adjacent rooms which are hosting laser labs. So this is basically where we got a laser lab from Oxford. We just need to drill a hole through a wall and can drive then basically the laser systems directly relevant for the 10-meter detector from there. So that's the plan. And in the first 30 months, that's the project duration, 30 months to 36 months, as a matter of fact, we promised to the funding agencies the following. The first thing was to establish the cold atom infrastructure across the UK. So that means really building, as I will show you in a minute, 5 ultra cold strontium laboratories in parallel based on similar specs in different places, which all will push the envelope of atom interferometer in different directions. We promised to the funding agency that we will have a full design of a 10-meter detector ready for physics exploitation. So it was very interesting to visit today the very large baseline atom interferometer here in Hanover to see how you have realized this 10-meter tower, what things will be required. It's certainly a good inspiration for us. And last but not least, not to forget, is to partner AION with the MAGIS experiment in the US. So MAGIS in the US performs a very similar program than we would like to do in the UK. And now they have decided to go directly to a 100-meter detector. So they're facing more engineering challenges, while we are looking more at the, pushing the frontier of cold atom exploitation. So these two programs are being very synergetic. And as a matter of fact, we are not only partnering on paper, but AION makes almost €1.5–2 million contribution directly to MAGIS, so that we really have not only, an in-kind collaboration, but a real hard product collaboration, where we have signed an agreement with them. So what we're planning to do now, and as we speak, this is going on, so the AION program now runs for 1 year, is to really push the state-of-the-art single-photon strontium atom interferometry. And for that reason, we're building 5 labs right now. So we built one in Birmingham at the Quantum Hub, one in Cambridge, one in Imperial College, one at Oxford, and one in Rahl. All of them are being based on similar specs. So for example, we have been having common designs on the laser stabilization system, where Richard has been very instrumental, but also on the ultra high vacuum system. But all of them have different specs a bit, because all of them will have to push different parameters. For example, Birmingham has committed to study large momentum transfer. Cambridge is looking at the launching of the atoms. Imperial College will be looking at squeezing of the atoms. And in Oxford, then the plan is to bring every of these things together, and Rahl also is then supporting it. So that's basically the plan. It's quite a comprehensive development program we have been putting in place. Each of them have a price tag of around £2.5 million to build up these labs. So it's quite an investment that's been done. And just to show you that it's not only the government willing to do an investment, it's also the universities which have been buying into the program, because we needed lab space to really establish these things from scratch. It didn't exist. So here I'm showing you what we have been doing at Imperial College. Now I should probably point out, Imperial College is located in the heart of London, in one of the, if not even the most expensive real estate area of South Kensington. Finding real estate there, like for example, 100 square meter to build a new lab, is extremely competitive, and you need a lot of support from the university. It costs a lot of money to do that. And that just shows you that we got 100 square meter, how much the universities are really willing to buy in. So that is already an in-kind contribution for more than $1 million from the university by itself, not coming from the funding of AION. And we are currently building up the lab. So we were taking it over, when was it, Richard? The lab? February, we took it over. That's the pictures when we took over the lab. So this is Richard and Charles, who are in charge of the AION lab, together with some students. It looks completely different today, because we have started to build the ultra high vacuum system and so on. But this is also now happening in all the other 4 places. Labs are being built up to the specs being defined. Now, as I said, we're taking this very serious. We're not just focusing on the R&D. We really believe in it, and we're already looking at sites to host a 100-meter detector after the demonstration of the 10-meter detector. And one possible site, besides the ones we are obviously still exploring in the UK, because at the moment it is a very UK intrinsic project. We have the Bolby mine and Dasbury, both of them are government laboratories as well. So there are options to build a detector. But there's another very interesting option, which I personally like a lot. It's namely to see if we could basically reuse some of the shafts at the LHC. So it's a Large Hadron Collider. CERN is the biggest, the biggest fundamental science laboratory in the world. And it's currently operating a huge machine called the Large Hadron Collider. But there's a lot of shafts that's been coming along. And there's one support shaft of an experiment I've been working before when I was doing my PhD, which is currently idle. It's not anymore being used. This is PX46. It has a length of 140 meters and a diameter 10 meters, is in a really well-established and clean environment. So since 1.5 years, we're working together with the CERN team, and they have made quite a bit of an investment to see whether or not that could be a valid site. So just as an example, there were seismic measurements being done. There are technical designs of how we could install, for example, a 100-meter detector and so on. And that was pretty impressive, and there's much more in the background. Now, the advantage of seeing this really as an international project is that you get along with it all the huge support the European Organization for Particle Physics, or fundamental science, if you like, could give us. I mean, CERN is the biggest fundamental science laboratory in the world. There's absolutely no doubt about it. It has an annual budget from the member states, which is more than €1 billion every year. It's a fixed budget which has been paid off and paid into it. And it is a very international endeavor, and it is meant to support fundamental science. Obviously, it's focusing on collider-based science, but there's nothing wrong of essentially proposing also other experiments which could essentially be established here. So these are really the core members in 1954. So in blue, these are the members which are basically controlling CERN, but there's a lot of associated and joint members coming along, which forming international collaborations. So that could be a very interesting, attractive route for terrestrial experiments to start building a more international collaboration and establishing cold atom technology as a means of technology for fundamental science. So the option of hosting a European-driven international 100-meter detector at CERN is interesting. I personally find this very interesting, but certainly the UK alone would not be able to pull this off because CERN requires international collaboration from the member states. So having, for example, people from France, Germany, also, for example, coming from Italy and any other European countries contributing to the effort would obviously be very, very helpful to convince CERN management to make a significant investment in such a technology development and eventually an experiment. Now, just to point out, and I will show you this a bit later, that this would not be just an empty thing in terms of pushing the envelope of the technology, a 100-meter detector. A 100-meter detector, if it really works up to the specs we have in mind, could already provide an additional second source of measurements for gravitational waves by 2030, because that's the timeline we are proposing. At the moment, the only experiment being able to observe in a given frequency range gravitational waves is LIGO/Virgo, or advanced LIGO. And this is the predicted sensitivity, as you can see it here. But a 100-meter detector could go and cross into the realm of sensitivity in a completely new physics range already by 2030. And who knows what will be out there, because you haven't seen that frequency range at all. So it's not a total empty thing. It's not only just you do ultralight dark matter with a 100-meter detector. No, you could already start opening up new parameter space for gravitational wave physics. Now, what makes me very hopeful that AION is not alone in the world and that there is a lot of other things ongoing is the fact that if you really look at ground-based large-scale terrestrial projects at the level of 100-meter who in one way or another make investments in cold atom technology, photon interferometry with the focus on fundamental science, maybe not exclusively, but significantly on fundamental science, then you find that, for example, MIGA in France is currently building, as we speak, a traditional rubidium-based atom interferometer with horizontal detection system. So really following laser atom interferometry, but horizontally. That's one prototype, 10 million currency units being invested in here. Then we have heard about SIGA, which has a hybrid approach. They both use rubidium and strontium. They are looking both on shaft experiments, as you can see here, as well as on experiments with the triangle. All of them are prototype experiments going towards gravitational waves and ultralight dark matter. I mentioned to you already AION and the collaboration with matches, strontium-based shaft experiments, which are very interesting. Each of them has been funded at the level of 10 currency units. And then obviously we also have the very large baseline atom interferometer here, which we just learned today, also has quite a bit of focus on fundamental physics, not only fundamental physics, but some fundamental physics as a driver and motivation. So there is a lot of projects out there today, which are either under development or close to finalizing to be developed, as for example here in Hanover, which all have an investment international level of 10 million currency units. So if you add this all up, we're looking at investments of 50 to 60 million as we speak now that are being realized on international funding levels. On national funding levels. There's no international project yet that could essentially really benefit from that. All of that is at the moment very done in the individual countries. And I think it may be time now to really gather up the masses and making this more in an international thing to open up more funding opportunities for the future. So that is basically about AION and a bit of pitching to come together in order to build a community also maybe for terrestrial detectors, not just for space. Now let me go a bit into the physics you can do with this, and in particular gravitational wave physics, because this is where I came from. That's why I got motivated in. So as I mentioned to you, laser interferometer detectors for decades now have been the choice of development to observe gravitational waves. It has been a long, long path. If you really talk to these people, I mean, at the beginning, when the whole technology development started, until they really measured them in 2016 gravitational waves, it was a very, very long route with lots of obstacles and with lots of challenges ahead, but it did work out. And eventually then 2016, LIGO and Virgo saw the first detection of gravitational waves. Wasn't really a big surprise. I mean, if you believe in general relativity, they have to be there. Now, the fact that we could see them really opens up a completely new realm of possibilities. Now, we have until 2016 hunted for gravitational wave detection as a discovery. Now they do become a tool, because it's a completely new frequency range, a completely new wave detection of this possibility, which you can use to learn about the beginning of the universe and many other aspects. So now we're turning this into a tool, not anymore a discovery, because we believe in general relativity. It has come together. So that was the big 2016 detection. Since then, gears have really shifted. We don't want to detect it anymore. We don't want to prove it's there. We want to use it. And in order to use it, we need to really make sure that we cover the entire frequency range and keep the comprehensive incarnations of gravitational waves. And that is where the problem now comes in. Because if you look at this plot here, which shows you the frequency of a gravitational wave as a function of the characteristic strain of the gravitational wave. Characteristic strain is, again, it's an odd measure by essentially saying I'm changing the length by so much with respect to the total length. So it's a relative change. There's better ways of characterizing the sensitivity, but if I'm as an outsider of that would propose a different scale here, then all the gravitational wave people would probably shoot me. So I'm not going to do this now. I have it in the backup for people who have been interested in, but that's one way of essentially characterizing it. Now, if you look at that plot, which I did in 2017, that's basically the landscape of what we are looking at if we're not doing anything. That one is running already and it's been extended. That one, Einstein telescope, is heavily debated, but it probably is going to come. LISA is being approved, and hopefully, if everything goes well, it's going to fly in 2035. So that's our gravitational wave landscape, if you like. Now, if you look carefully, and as we would say in London, I would say mind the gap. There is a huge gap in the frequency range, which is totally uncovered. Now, if you really want to use gravitational waves as a tool, gaps in your frequency range are the worst thing you can have. So when I looked at that, I was trying to look for technologies of how to fill it. And there's a reason why laser interferometry is not filling that gap, because it's really hard for laser interferometry to fill that gap. But on the other hand, atom interferometry and some modest predictions or reasonable predictions for a kilometer scale detector, for example, would already almost completely fill that gap. So already by 2035-ish, when we could build a kilometer detector, because it's just scaling from a 10 meter to 100 meter and to a kilometer, assuming you have the appropriate shaft, you could already be a big player into gravitational waves and cover this mid-frequency range. Now, it does not look so exciting in terms of why to cover the mid-frequency range, but there is something which many people forget about the mid-frequency range, which is very important, namely the lifetime of the signals and the sources you observe. If you remember, and I've ever seen gravitational wave detections of LIGO and Virgo, these are little chirps of microseconds where they see a signal and they have to essentially correlate it between the two different detectors. It's a very short amount of time. There's a signal, and then you know there was a gravitational wave. So essentially then using this gravitational wave to make sky determination where it came from to do multi-messenger physics is hard, very difficult. The mid-frequency range, however, is very different. If you have an experiment that operates in the mid-frequency range, then the signal you observe, the lifetime of the signal is days, weeks, and months instead of milliseconds. That's just by the nature of the evolution of the gravitational wave signal. Now, with weeks and months, I can use rotation of the Earth around the sun to do sky determination where the signal is coming from, because I have days to figure it out instead of just a millisecond. Now, in order to do that, we have been studying a couple of the primary discovery signals LIGO and Virgo were doing to show how accurately you could determine sky determinations. And there's a lot you can really point down. So with that, you could all tell all the telescopes and anyone who wants to look at it, electrons, photons, or something, look at that. There's a signal coming in whatever, couple of days. Be ready for it. And we would learn an enormous amount of this multi-messenger physics. Very hard to be done with LISA, because LISA lifetime sources will be years, hundreds and thousands of years in that frequency range. LIGO, Virgo lifetime, so Einstein telescopes will be milliseconds. Mid-frequency range is when you have days and weeks, which is good for essentially doing sky location and multi-messenger physics. Obviously, you can further improve if you're operating a network of those detectors, as we are planning with matches and AION, like the LIGO Virgo style network. Also, that is something which is very helpful. So going back to that plot, that is something we could do with quantum technology, assuming we really demonstrate that such a detector to that specifications can be built with atom interferometry. But obviously, ultimately, what you would like to do is you would like to bring it to space. Because even with some modest assumptions about the space detector, and that's been shown here in blue, you could really cover even more very interesting real estate in the frequency range. So the terrestrial detector would be a stepping stone towards it, but ultimately you want to bring it to space. And that is obviously where a lot of our efforts also have been working in, because we do see the AION program, as I pointed out to you before, as a stage program with terrestrial detectors being not only pathfinders to a space program, but also experiments which can do and provide already some physics. But ultimately, we want to go to space. So organizing a community that is willing to support the idea to bring cold atom technology to space is extremely important, because that's the only way how you will get sufficient amount of money, how you can convince space agencies like ESA or NASA to really make an investment. You need to have a significant community behind it. And in 2021, we started out after the announcement of the Voyage 2050 call from ESA and the recommendations from the senior committee, which in particular embraced the idea of cold atoms in space, to organize a community and ourselves. And if you look at the organizers here who have been coming together, you can clearly see a couple of names which are very familiar to you from your field: Peter Wolf, Tino, Christian Schubert, Stefan Schiller, Ernst Russell, and so on. You just go through the list, and there will be several people you are probably familiar with coming from the cold atom community, but there's also a lot of other people you might not know, and these are then from the really what we call user community or fundamental science community, like myself. So we had an interesting workshop. Don't want to go too much into the details, but just to show that it was not only about fundamental science, it was really trying to cover all the bases of how to get cold atoms in space, and that includes, for example, also Earth observation, and clocks in general, and so on. So we really had an interesting workshop, which essentially in red was covering everything related to fundamental physics. In green, we also had representations from basically all the national space agencies, including ESA and NASA, being coming to the workshop, giving us their view of how they think we should organize ourselves in order to really, convince them that this is a way forward to buy into a program. And there was a lot of other things we have been discussing, like, for example, atomic clocks in space, where Richard has been one of the people leading the discussion, but also Earth observation, which I was just informed. Now, so you said today you got 17 million for this European project to develop a Pathfinder concept for an Earth observation mission with utilizing rubidium atom interferometry. Yeah. Not a Porsche today, no. So we're writing this all up, because that's also very important. You have to write it up. You have to make sure that the agencies do understand that you are there and that you are doing it. So we have been writing this up in quite a comprehensive document for those who's been interested in. So 250 scientists have been signing it, various different things, half of them coming from, I'm sweating a lot here, sorry for that, coming from the field of cold atom technology. But most importantly, and that is what funding agencies like, we give them a roadmap. A roadmap, how we think that cold atoms should be deployed to space. Now, it's obviously at the end of the day up to the funding agencies whether or not they buy into it, but it has a lot of weight once it comes really from the community they are meant to support. We have gotten very good and positive feedback from ESA already, and also NASA has embraced the whole thing. I'm not going to go too much into the details about this roadmap because it's pretty complex, and bringing this into one page has been a big challenge for me. I've spent weeks on that. But the important aspect I want to discuss with you now is that when it comes to fundamental physics, I think there are three main interesting milestones in that roadmap. The first one I mentioned to you already, that's the terrestrial pathfinder program, like AION matches, but also VLBAI. And then there are two missions, big missions, based one on rubidium, one on strontium, which are purely fundamental science exploitation. One is the so-called STE-QUEST mission, will be an M-class mission, which has a price tag of 500 million. And then eventually AEDGE, as I showed you before, for the ultimate sensitivity for gravitational wave, which is an L-class mission, which is the same price tag that LISA. So it's around 1.5 to 2 billion currency units. Now, a bit more about those as we go along in the talk. Let's start with AEDGE, which to some extent sits at the end of the timeline for good reasons. It's really 2045 because it is a very ambitious proposal. I mean, bringing technology to that stage will take some time. But it has also been to some extent the starting point of that community building process, because in 2019, we were calling this AEDGE workshop as a response to ESA asking for white papers to be submitted for Voyage 2050. And we were just, been finalizing the AION proposal. We thought it might be a good idea to think about going into space. So we had a couple of people coming together, and we were really surprised about the success of this workshop at CERN, because we had, that was still in-person workshops. I mean, that was before COVID. So we really have 130 participants, and we're maybe expecting 40 or 50 or something like that, coming to CERN, actually in person to CERN, to really discuss the opportunities. So there was a huge interest in something like this, and we have been writing this up. And since then have submitted it to ESA, and ESA has given us very positive feedback. They do realize that that's obviously not something they can build now, but they like the idea of a vision forward, in particular when we're talking about Voyage 2015, because it's nothing but visions forward, because that program will be realized in 2 to 3 decades from now. So what did we propose in that? We were basically proposing the same setup I already introduced to you, namely a space-based version of AION, if you like. So there will be 2 satellites. Each of those satellites will be hosting an atom interferometer sequence, relatively modest atom interferometer sequence, as a matter of fact, but they will be separated by a rather long distance in mid-Earth orbit of around 10 to the 7 meters. And that's where a lot of the sensitivity comes from, because simply by the separation of the 2 satellites, because it scales linearly with it. So that was very important. And the other one, which has actually been led here in-house in Hanover, is STE-QUEST. That would be something obviously that comes closer in time. It's a mission which has much higher TRL level. And it is something which we are currently just working together to put the proposal together under the lead of Nasser and Peter Wolf in France. So people from the UK like myself have joined the core team to help supporting this towards the UK funding agencies. But I think it is a very strong proposal. And it is again being supported by this community building process of saying, well, this is a major milestone we as a community think should be realized towards the full exploitation of cold atoms in space. It is, as I'm sure you have heard many times from Nasser and others, been based very closely on many of the aspects you guys are doing here in Hanover. I mean, it's basically dual species atom interferometry based in rubidium and potassium to achieve sensitivity levels, as you can see down there, around 10 to the minus 17. Ambitious, but certainly not impossible. But ambitious is something you have to have if you're asking for 500 million. To be supported, and the idea would be it would be flying around 2036, 2037. So we're putting a lot of effort into that proposal right now, and it has really very interesting physics applications. It wouldn't be able to measure gravitational waves. It's not meant for that, but it has a lot of interesting aspects when it comes to ultralight dark matter, when it comes to collapse of quantum mechanics, and in particular, and that has been the initial proposal and driver for the equivalence principle measurement. But there's a 3-pronged scientific program to it, which is really, really appealing. And we will see how ESA is responding to it, but I'm pretty hopeful that maybe not the first mission will be selected, but I'm sure that in the next missions then which come, there will be 12 of them in the next 2 decades, if I'm not mistaken. 12 they promised, yeah, 12 M-class missions. So I hope we're doing very well by that, maybe already being selected. If not, I think we're going to try it in a couple of years again. But hopefully it will be now. Now back to the science. So this is where we have been leaving it with a space-based version. But if you're now really being ambitious and put everything together, then that plot, which I showed you before, which had these lots of gaps and everything in there, that plot in 2045 could look like this. And that's the vision I think we have to present towards the funding agencies, towards our communities, to really be able to sell that program. There's a lot of stages in there. So there's a 10-meter detector, there's a 100-meter detector, there's a kilometer detector, there's a space-based detector, and there is a very aggressive space-based detector, H+, which even then later could basically include the entire frequency range that LISA is covering. Now, I want to make sure that this is not in competition. We are not competing with Einstein telescope, or we're not competing with LISA, because these are completely different timescales. We're proposing follow-ups on those programs, which could be based on quantum technology, and then basically covering a much larger parameter space comprehensively in one mission profile. It doesn't make the others obsolete. Now, there's much more you could do with gravitational waves. We have been writing this up. There's a lot of interesting things you can do by first order new physics phase transitions that could have happened at the beginning of the universe, cosmic strings, all of those are generating gravitational waves, which you can measure. I mean, this has all been written down there. So there's a lot of interesting physics you can learn from gravitational waves once you have comprehensive access to the frequency with sufficient sensitivity. Now, quickly to dark matter. That's another very interesting aspect. Now, personally, I have spent, after the Higgs discovery at CERN, where I've been involved, we spent a lot of time searching for new physics particles outside of the standard model, besides the Higgs, obviously, which is part of the standard model. And dark matter candidates, either in supersymmetry or outside of supersymmetry, have been the prime target for more than a decade to look for. And that has been one of the reasons why we built that machine, besides the Higgs discovery. But I can tell you, having spent 20 odd years on searching for those, we haven't found anything yet. And we really reached the point where massive dark matter, as it's been labeled here, has been explored to a level where I think it is time to really comprehensively look at alternative options as well. So our prejudice and prior we had for example, weakly interacting dark matter seem not to have been realized, and we have to acknowledge that. And I find this ultralight dark matter, where essentially now you're using, the matter wave duality with quantum mechanics give you to characterize this in two different things. It's never 100% accurate, but if you look at ultralight dark matter, then you really can see these instead of particles as waves, as I was just introducing to you. And there's an even larger parameter space that is allowed for ultralight dark matter. It really goes over many decades of mass or frequency range. And if you look at just this mass range, then there must be many different means of exploring it. But one interesting means is certainly atom interferometry, like the one we are proposing in MAGES and AION. It can cover a very large range of parameter space. So could, for example, STE-QUEST with the dual species and so on, that would be part of this as well. But it's not the only tool we would use in order to search for ultralight dark matter, but it is an important one, which can be, again, made a good case for that. And possibly there are big discoveries in there. Just to give you the example, what is behind that, I mentioned that to you already. The idea for ultralight dark matter, in particular, if you think of it like a scalar dark matter now, would be there is a halo of dark matter, which is basically informing the galaxy formations. This is what makes it actually quite interesting, which is basically surrounding us all the time. It's penetrating us as a wave character. So it's here all the time, it's going through us as a field. And that field then interacts with our standard model Lagrangian and imprints the frequency, which is determined by the mass of the dark matter candidate, on the fundamental coupling constants for the electrons and the photons. And that's then, as I mentioned to you, the way how we can measure it in the atom interferometer sequence by comparing the two. Now, to show you that this really gives us again, like for gravitational waves, a huge program to go through fundamental physics exploitation. This shows you again now the evolution for scalar dark matter for different couplings. Don't want to go too much into the details. That's what a 10-meter detector could do. That is what a 100-meter detector could do. Here you see the dashed line is what ST-QUEST, for example, could do if it would be flying with dark matter. Then here you have a kilometer detector, and obviously, ultimately, this is what AEDGE could do. Now, you could here complement this atom interferometry also with some interesting aspects from atomic clocks. So they're actually quite synergetic in terms of covering even more parameter space. This is not being shown here, but just by this atom interferometry, there's a lot we could cover already with this dark matter. And plenty of other fundamental physics one could conceptually probe with these atom interferometers and possibly also the extensions to atomic clocks. We haven't really thought much about it because at the moment we are focusing on making the physics case for gravitational waves and ultralight dark matter, but there's a lot of interesting other aspects one can do. And I think I just leave it here because I probably have taken too much time anyway. So that's the summary. I just leave it for you to read. Thank you.